Hey everyone, I just my brain stopped working for a second. So now, if we decide to solve for v in this equation, v equals m over d via the whole switcheroonie method, um, I'm going to plug this in. I just want to derive the equation for density of a gas. That's all I'm doing. So I'm going to plug this in for d here. I mean for v. Okay. So then I get P times M over D is equal to NRT. Okay, so then I'm going to do a switcheroonie, all three of these things. Okay, all three of these things, I'm going to switch with D, boop, boop, and I get D is equal to pressure times mass over moles times the ideal gas constant times the temperature. Okay? Now, if I want to simplify this equation here, mass over moles is the mass of 1 mole of something is the molar mass. So I'm going to say the density is equal to pressure times molar mass over the ideal gas constant times T. And this is the equation for density of a gas that we are going to use. Okay? Now, when we use this equation, the ideal gas law, okay, there are some assumptions about the gas that we have to make, okay? And we call that kinetic molecular theory. So kinetic molecular theory is a set of assumptions we must make about a gas for it to behave in an ideal manner. Okay? So, in no particular order, assumption number 1 states that we assume that gas particles have negligible volume. So what that means is when we talk about the volume of a container, they do not take away from the volume of the container that they occupy. Okay? So whatever, if the volume of the container is 2 liters, then it's 2 liters. And no matter how much gas is in there taking up space, we assume that those gas particles have negligible volume. Okay? Number 2 is the attractions, or I should say there are no forces of attraction between gas, I should say attraction or repulsion between gas particles. Okay? So they do not affect each other's motion, okay? When they collide, okay? But they do not when they're not touching each other, they're not affecting each other at all. Okay. Number 3 states that collisions between gas particles are perfectly elastic, meaning there is no loss of energy in the collision. Okay, get one more thing, or 2 more things. Gas particles move in straight lines. Oh, no. Randomly. Until they hit the walls of the container. Or each other. Okay. And lastly, and possibly the most important thing, is that the temperature is the only thing that affects the kinetic energy of the gas particles. Okay, so those are the assumptions that we have to make about gas particles for them to behave in an ideal manner. Now, if we start talking about ideal versus real gases, in order to behave like an ideal gas, the gas molecules can't have any volume. We talked about this. So certain conditions are not conducive to ideal gas behavior. So when is something when does a gas act as a real gas, and when does a gas act as an ideal gas? Okay, when they act as a real gas at low temp, high pressure, low volume. Okay, they act as ideal gases at the opposite of this, high temps, low pressure, high volume. So when we think about some of the requirements for and some of the assumptions that we have to make with kinetic molecular theory, one of them is that they don't affect each other's motion. Okay, now when are they more likely to affect each other's motion? When they're moving really slowly, or when they're moving really fast past each other. Okay, they're more likely to be attracted when they're moving really slowly and they have time to form some sort of attraction and change their course of motion. Okay, so that's when they start acting as a real gas, when there's a very low temperature and they're not moving as fast. Also, another assumption we make is that their volume is negligible. Now, if we have a container with a really, 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 really small volume and we have tons of gas particles in there, okay, so we have a small volume and a really high pressure, then the smaller the container, the more the less negligible the volume of the gas particles can actually be because there's less space. Okay. If we have a really high volume, a really large container, then gas particles aren't really going to factor in to the volume of that container as much. Okay. So if you want to picture it like this, if I have a really small container and I have tons of gas particles, let's say 10, I think that was 10. I have actually no idea, but this is a low volume. So you can see these dots, there's less space here, okay? Now, if I have a larger container and I have 10 dots, okay, they take up less of a percentage. These gas particles take up less of a percentage of the total volume than they do in here, okay? So these gas particles take up a smaller percentage of the total volume as these ones. So these are more ideal conditions than this, okay? And that is going to be it for today. We'll talk about Dalton's law of partial pressures and Graham's law of effusion next class. Have a wonderful rest of your day, everybody. And don't forget to do the homework that's assigned today as well.